Hello. So this talk is on MLIR dialect design, which is conceptually a very broad topic because dialects are like the building blocks of MLIR compilers. So the quick agenda of this talk is we're going to focus on the role of a dialect. Like what is it that you want a dialect to do? Dialects can do conceptually very many different things. We're going to start from a high level, we're going to zoom out and do a high level overview of like MLIR compiler architecture, building compilers, the whole view of an MLIR compiler, which if you're doing it right, should have more than one dialect in it. We'll then get into like taxonomy of dialects. There's different kinds of dialects, they do different things, they have different roles, and so you design them in different ways. And we're going to break this down into some like principles, rules of thumbs, trade-offs, and get into some case studies of the real dialects and how they showcase some of these examples. What we're not going to focus on today is like how you implement a dialect. Dialects you can think of as more of a specification, right? So like what ops, what types, what are their semantics, what are their operands? And so not like, how do you actually write lowerings and write all the parsers. We're also not going to focus much on dialect syntax of operations and stuff. I'll pass it over to Mehdi, who's going to talk about why we actually need dialects.
Thanks, Jeff. So why do we have dialects? So as everyone knows, dialects in MLIR are a logical grouping and like a namespacing where you can define your types, your attributes, and your operations. And I often say that dialect design is to compiler what library API design is to software. You can design a compiler as a big monolith that takes as an input a very high-level LLVM and emits directly assembly. You can imagine machine learning compiler like XLA taking directly mathmul operation and trying to emit x86 assembly straight in one pass, one go. The problem is maintainability. The problem is how to understand if in one shot you're taking big operation and emitting directly a very low-level concept. There is very little you can reuse, very little modularity into it. And this is not specific to compilers. This is the same for any software project. Most software project, we're going to try to divide the project in chunks that we can understand, that we can maintain, that we can reuse, that we can document, that we can test. And in software, those are library design. In compilers, in MLIR compilers, at least this is dialects. And so the same kind of principle should apply to software design here in compilers. And so the genesis of this talk is that we started to think that in software design, we have principles. They have been studied for decades. There is design patterns, what is a factory, what is a singleton, what are all those patterns. We don't have this for MLIR. And to manage the expectation, we're not going to come here today with like a new book with design pattern for MLIR dialects. We are just scratching the surface. But we are trying to get in this direction, right? It's still very early work, and hopefully it's going to spark some ideas here. And so what makes a good dialect? So dialects fundamentally, as Jeff hinted, are specifications. They provide contracts. They define semantic of the operations, the attributes, the types. It's all about design. There's not a right or wrong answer. There are lots of trade-offs. The quality of a dialect design is often to be judged in its role in an MLIR compiler. So you have to understand the context in which a dialect is supposed to play and how it's going to interact with other dialects. What we found in dialect design in MLIR is that the types are more important than the operation. At least they are less malleable, meaning over time, as a compiler evolves or as you try to reuse dialect, what's really difficult is the types they operate on. Because operations can always evolve. You can always try to change operation, add more operation to a dialect, or use different sets of operations. But to interrupt with the rest of the ecosystem, the types are really, really important. And so there is probably more attention that should be given to types when we design a dialect than to operation, at least at the first step. So we looked at various MLIR-based compilers, and we tried to identify some components in a compiler. And when we work on compiler projects at large, especially MLIR-based compiler, frequently we try to import something first. Like if you build a new language, you may start from an AST. But if you interact with an ML compiler, you will gonna import a graph or the internal representation of the tool you want to interact with. So some presentation about decompilation or bytecode. So your input is gonna be the bytecode format. And so frequently in MLIR, you're gonna build a dialect that is almost one-to-one to the input, or that is gonna simplify this import phase. Then there are like some sort of funnels. If you build an optimizer or a compiler, you may have multiple inputs. And so those, after you import, you're going to try to funnel into a common representation. For example, in MLIR upstream, you may have seen linalg, and linalg is a good funnel. You may start with a TOSA dialect, which models some ML ops. You may start from XLA-HLO. You may start from various representation, and you're going to funnel into linalg. And that's going to simplify the next components, which is how you legalize, how you start getting into this common representation. Many dialects can be involved here, but just to get to the optimizer. Then you have levels where you can do your optimization, and regardless of the input, the original input, whether it was TOSA, whether it was HLO, whether it was, when you get into this abstract representation, you funnel into it, you have an optimizer that is simpler. You don't have to re-implement multiple times the same concepts. And then at some point, it's time to specialize. Specialization is when you start getting towards the output, towards the target. For example, you may have optimized, generated the abstract vector dialect, but you start thinking, I'm going to target ARM scalable vector, or I'm going to target NVIDIA GPUs, and I'm going to specialize with all the new shiny feature of the GPU generation I'm going to target. And some dialects may be needed to expose those concepts that are specific to your target. So it's the fan-out phase before reaching the export, where you start getting into an external system. The natural export is often LLVM, for example. And so, again, there's a dialect that might be involved, or a set of dialects, to export towards LLVM or towards another target. And Jeff is going to give you some example of compilers and components there.
Right. So thanks, Mehdi, for explaining the pieces of an MLIR compiler. Here we have one slice of the massive ecosystem of interconnected ML compilers and dialects on the TensorFlow, or on TensorFlow. So we start from the graph dev. This is that's what comes out of the Python API. You have a protobuf-based representation of the TensorFlow graph with ops inside of it. The graph dev importer can target the TFG dialect, which is the TensorFlow graph dialect. This is the importer that we've seen. And then we have a legalizer that converts TFG to the TensorFlow executor dialect down to just the TensorFlow dialect, and then all the way down to MHLO, which is sort of like conceptually a mid-level dialect in this architecture. And then we have an optimizer at the MHLO level, which starts to introduce new dialects. And importantly here, a dialect or a logical unit or logical collection of operations in the IR can also be composed of multiple individual dialects, this hybrid representation. Typically, they share a type system, which binds them together. And then, from here, there's like many paths you can take. You can go out to stable HLO, down to regular HLO, and target TPUs. You can export to TOSA, and then use all the TOSA accessible backends. But in our example, we're just going to go from NHLO to this linalg on tensors representation, which is typically composed of the linalg dialect, the arith dialect, SCF dialect, vector dialect. Here you can do you have progressive lowering and optimization of the IR. One of these things is the bufferization task, which actually introduces a bufferization dialect that exists for a while, then it disappears. And then you even have the transform dialect that we generate the schedule, we run it, and then the dialect goes away. So we have all these little short-lived dialects that come into the compiler, play a role, and then disappear. And then from here, we can export to the GPU backend, to LLVM, and GPU allows you to access NVIDIA and AMD GPUs. So here's another diagram that Alex Sinzanenko produced several years ago that is kind of like an overview of the upstream open source dialect ecosystem circa 2019. And if you kind of like, you can kind of like see, there's a bit of a legalizer here from MHLO to linalg, what was previously known as the standard dialect, and LMHLO, which is like HLO but lower. There's an optimizer phase here with linalg, affine, SCF, and the shape dialect that is introduced and again disappears after optimization is over. A funnel from here from both Sphere V and LLVM targeting this from various different dialects is like a funnel. And a specializer where we go from SCF to We raise loops to OpenMP or OpenACC, and then also even like parallel loops become async dialect representations. Here's a more updated but kind of incorrect version of this that incorporates some of the newer dialects. And what we can see is that the Arith dialect has kind of emerged as this funnel, even though arguably it shouldn't be. Here's the very well-designed diagram from the Erie GitHub page that probably many people are familiar with. And if you look at this, you can see the common components. There's an import layer that takes PyTorch, JAX, TF, everything else, et cetera. And then this gets funneled into a common input representation. It goes into an optimizer box. They have the flow dialect, the stream dialect, and then this eventually boils down to the HAL dialect, or hardware abstraction layer, which then gets specialized to LLVM, emit-C, VM, which is the IRE runtime. And then I thought this was an interesting example, is to look at Fortran and Flang, because until recently, I didn't actually know about Cyclone. You'd think of Flang as like sort of a self-contained system. So yeah, it has a lot less branching and interconnected pieces that a big ecosystem would have, but you still have the common components. You have an importer, the parser, ASD, from Fortran source code. It spawns this big collection of different dialects from upstream, including some Flang dialects like HLFIR and FIR. It gets lowered down to a more reduced representation, and I've omitted some of the dialects here. There's an optimizer phase that like raises some loops to affine dialect, runs the optimizer, and then lowers them away, does some like math algebraic simplifications, and we legalize all of that down to LLVM. Then there's an exporter. Here's even Circuit. Circuit, which is a hardware compiler, which is conceptually a little bit of a jump from the normal compilers we've seen. Even Circuit has the same structures. There's an import layer, there's a funnel down to the RTL dialects, which is a progressive lowering, optimizer, and legalizer, and then an export layer to all the different kinds of fun hardware formats that you have. I also found this one online. This is like a hardware software co-design compiler where you both produce the LLVM and like the hardware specification at the same time. Again, import layer, MLIR, export to LLVM, and the hardware. And you may notice that the same structures that we've seen, import, exporter, funnel, et cetera, there's like self-similarity in and out, right? If you look at a funnel, there may be, components. If you look at a legalizer, there's funnels and short-lived dialects within them. You zoom out, even the whole compiler itself, you can argue, is like an hourglass.
Yeah, so after all those examples that illustrate those components, we circle back to it, and we hope that we made the point that dialect design starts by understanding the problem you're trying to solve, positioning them in a big picture, and thinking about why you introduce a dialect. It's because the abstraction exists naturally. We learned this also looking into XLA and the XLA compiler, which traditionally takes those high-level ops and emit directly LLVM IR. The C++ implementation that exists in some XLA backends is actually fairly complex. And naturally, as we refactor them, we start building abstraction and figuring that there are likely a dialect that should exist here naturally. And so dialects solve natural problem when we start having problem and we decompose them. So what we did here is we started thinking about a taxonomy of dialect and thinking about what kind of properties we could adopt with those categories. And so we identified those 8 categories of dialects: input, hourglass, optimizer, computation, output, paradigm, glue, and meta. And we're going to go through this right now.
Right. So let's say we take a look at input dialects. Right, input dialects represent the target of an importer from an external format. This can be GraphDef to TFG, safe model to TF safe model, PyTorch to Torch and Torch MLIR, and Onyx to the Onyx dialect and Onyx MLIR. And then here's some slides actually from I don't remember even when it was, but there's an Erie ODM where they talk about this input dialect. And Erie has this sort of input layer architecture where they take their input formats, TensorFlow, TF Lite, JAX, and they immediately go and generate a large collection of internal dialects. And then they talk about how this is actually like not a very good architecture. They want to introduce a new waistline, and then they target this common waistline and then lower to their internal dialects. And the internal dialects are also like a moving target because they shuffle around, they change the R based on the role those dialects play, which is also to be optimized. So the goals of an input dialect is you want to capture all the semantics of the input format. It should be easy to target, and so the converter should be relatively simple logic. we don't want any loss of relevant information from the input format, because if you're losing information, that's also lowering. And it should also hopefully be structurally similar to the input program. There's some rules of thumb, like one-to-one, where each graph type gets one operation, and each thing that exists in the input format gets some kind of representation in the MLIR. And importantly, it should not really be a funnel, because again, if you want to funnel in different input formats, there has to be a loss of information that happens. So one example of this is the TensorFlow graph dialect, which is very closely to be a one-to-one mapping of graph depth to TFG using MLIR concepts like attributes, graph regions, and like using unregistered ops to capture all the TensorFlow ops. And the dialect itself only contains like a small number of structural elements like tfg.graph, tfg.func, and return. But it also maintains the semantics or the representation of the semantics in the graph depth, which is like functional control flow.
Well, let's talk about Hourglass dialects now. So those Hourglass dialects are kind of looking up and down. Looking up, they are providing common abstractions over some concepts, and looking down, they are supposed to provide an easy way to specialize them. And we identify some example of Hourglass dialects. I mean, even originally, one of the main Hourglass model in compiler is LLVM itself. LLVM provides historically to language an abstraction to target the LLVM IR with the promise that it's going to then make it easy for a new hardware vendor to plug into it. And so the service that we provide here is an easy pluggable point both up and down, service to front end and a service to the back ends. And there are a few examples in the MLIR ecosystem of dialects that are trying to serve this purpose. At least that's one of the purposes they serve. And that influenced the design of the dialect when we understand how it's positioned in this context. So some of the goals of Hourglass dialects, I touched on them, right? It's exposing this convenient API interface, exposing the capability of the hardware, but not overly specialized, because otherwise you lose the abstraction. So those are trade-offs to make. And so often you don't expose all the capabilities of the target, but you try to provide the escape hatch, like power users that wants to target the vector abstraction, but still need some specific intrinsics, should have access to it. And then we get into composability. The vector dialects may not offer all the possibilities of every vector implementation. And for this, you have to sometimes get around it. So trade-offs. And dialects design is a lot about trade-offs. Another example is GPU dialects, right, which we try to expose as much possibility, as much capability like the tensor cores or those kind of things, but you cannot be overly specialized if you want to keep this Hourglass capability. And so the design of the GPU dialect is very influenced by this desire to abstract the various platform while allowing the users still access to some specificities of the target. If we release a new GPU with some new very specific capability, you still want the user to be able to take advantage of it when the GPU dialect cannot just abstract it. And we have other example of way to do that, right? You supplement the GPU dialect with NV GPU dialect and AMD GPU dialect to expose specificity of the platforms. But let's move on to optimizer dialects.
Right, so optimizer dialects are one goal, and typically an entire MLIR compiler is built around an optimizer dialect, because what's the purpose of compilers is to make the code run fast. And the really only purpose of these dialects is to provide a convenient representation of the program to be optimized. So the goal is to do that. And some of the criteria is that you really want to boil these concepts down to a small number of operations. So it's easy. You really want to have the concepts are neatly contained, and that hopefully it's pluggable and extensible. If you've built a nice optimizer system, maybe you want other people to use it, or maybe it doesn't just optimize your specific domain. It's not a domain-specific application, but a generic application. And so some of the principles would be you don't really have a lot of ops. You really want to have a minimal number of operations in the dialect. Otherwise, your optimizations are complicated to write. And then it should be designed for transformability. The layout of IR constructs and types, attributes, and ops are supposed to be intentionally easy to manipulate in the C++ code that writes the optimizations. So one example of this is the LLVM dialect, which it's been going through a lot of transformations over the year. But if you really look at it, there's only a handful of ops. There's the main one, LLVM generic. There's a terminator, and there's a few other ones that sort of play a role in the dialect. There's also like this Linux structured ops, which has like a ton of different ops, but they really are just Linux syntax sugar for Linux generic. I'm going to pick on a specific example of this Linux dialect operation. It has this like relative indexing loop scheme where it's like, give me the loop index of the nearest end loop. And you may wonder, well, why not just have like an SSA argument value? Well, if you're moving this code around and adding new loops and swapping them in and out, you don't want to be doing these SSA value replacements. All you care is that at the end of the day, when all the loops are done and your code is where it's supposed to be, lower it to grab the nearest index. And this is part of the design for transformability. The goal of this operation is not to like, I need to know that for sure that this is this operation's block argument. It says, I just care about the nearest index. Then we look at computation dialects, which are kind of like the meat on the bones, right? These are the number crunching operations inside a compiler. There's not really anything special about them. It's kind of hard to mess these up. But ideally, you want each operation to be a self-contained capability, and that they should really be like 1 to n lowerable, that you don't have like 2 ops together, or is the only possible way you can lower an operation. That means one of the ops on its own doesn't do anything, which is not a good abstraction. One of the not so great examples of maybe a computation dialect is the EuroLLVM dialect, and this is again the slow death of the standard dialect. It's got some scope creep in it. You can do scalars, vectors, ND vectors, tensors, right? And so really like the scope of the capability has grown beyond what each operation should conceptually do. And then we have paradigm dialects. Paradigm dialects are like the bones, right? These provide structure to the IR. They implement some kind of paradigm or programming model, but they typically on their own don't do anything. If you just have the SCF dialect, your program doesn't do anything. If you just have the Linux dialect, your program mostly doesn't do anything, right? Minus like the structured ops. Func also on its own doesn't do anything. It's just the bones. But paradigm dialects really implement some kind of structure that gives the computation, the optimal computation dialects like higher level meaning. And so the criteria for this is that, again, a small number of operations that provide a precise representation of a programming model or concept, and it should be easy to compose with computation dialects. One example of this is the async dialect. Async dialect is weird because it's actually like 4 dialects concatenated together, but you kind of just like take the top off. There's a small number of operations and a type, which is, I think this is an interesting example. Async execute, func, and call are sort of the same thing of like, here's a region, run it somewhere asynchronously, and then it returns an async value that you can go and wait on later. So here's an example of you have an async.execute. You can put any code you want inside of it. It composes with any dialect and type, because you can wrap any type in an async value, go do some stuff, and then grab the value out later. They can have multiple implementations of this dialect as well. It doesn't have to be implemented on the coroutine runtime thing that it is right now.
All right, and now on output dialects. And output dialects, as the name indicates, is when we somehow exit MLIR, when we reach our target. Often we think about LLVM as the output dialect of MLIR, but there are others. SPIRV is an interesting example also when we think about design, and SPIRV has been on many slides because it's involved, depending on the compiler and the project, it can be an input dialect or an output dialect. You may have a compiler, an ML compiler that will emit SPIRV kernels and store them as the ultimate output of the compiler. But for someone who implements a platform, they will consume SPIRV, and so SPIRV will be their inputs before they implement their compiler through their ASA or through their accelerator. And so some of those dialects are playing multiple roles, and that influences their design as well. Thinking about, in different contexts, what are the different constraints and making the right trade-off to serve this. So we have many output dialects here, but this is very context dependent. In general, the goal is to map to something external, so there are strong constraints on an output dialect that are not, there's the design of the dialect, but often it's also not, you're not totally free in what you want to do. The SPIRV dialect, for example, match the SPIRV specifications. The LLVM dialect is fairly close to LLVM. We have to be making it convenient to export. And dialects like SPIRV that acts as input format and output format has to be one-to-one to the external format, because if you can have some leeway when you have a pure output dialect where during the conversion you can still do some adjustments, you may not be able to do the opposite, so you may lose the import capability. So if you want to round trip, then you probably want to be almost one-to-one. But in general, the dialect abstraction is at least as high as the external format. So LLVM is also an interesting example. The LLVM IR has grown over the years, and LLVM doesn't have really dialects. LLVM IR tries to model everything. And so really, in MLIR, at some point, we felt that LLVM is almost too large. So the LLVM export infrastructure is pluggable. An example of this is that depending on the kind of hardware you target, if you're targeting NVIDIA hardware, you may use the NVGPU dialect to expose the intrinsics, and that can plug into the export. So when you convert from MLIR LLVM to LLVM IR, you may have a mix of dialects already that will together translate to LLVM IR. So if you think about everything that LLVM can models, LLVM plus the intrinsics plus the OpenMP abstractions, in MLIR, this is already a composition of multiple dialects. We had to decompose it. For example, OpenMP is another good example. The OpenMP dialect plus the LLVM dialect can directly translate to some LLVM IR. And you may lose some capability to import. For example, we cannot reverse the transformation that is done when we export the OpenMP dialect to MLIR, because that inserts maybe outlining in the process. There are lots of logic that is done and exposed by the OpenMP builder in in LLVM. Other examples are constants. So this is reversible, of course, but we have to adjust between the way we model constant in MLIR and the way we model constant in LLVM, and so we make trade-offs here, and we hide the complexity in the translation. Jeff wants to talk about meta-dialect.
Yeah, so there's one last, second last category of dialects are this interesting new meta-dialects. These are dialects that implement parts of the compiler themselves. PDL does rewrites, IRDL does dialect definitions, and the transform dialect does schedules and path transformations. It's kind of hard to really figure out what makes a good meta-dialect because there are only 3 in the world, as far as I know, and they're kind of a young concept. But ideally, they should neatly expose MLIR core concepts and constructs and model their semantic, like operation types and attributes. Finally, we have glue dialects. Glue dialects are a bit of a catch-all category, but typically they play a role of binding dialects together. This can be like the built-in dialect, which defines types, not really a type system, but many dialects use those types, and they can all interrupt together, most of the time, right? And some of the principles of a glue dialect is that they have a small interface of operations and types to allow dialects to talk to each other, maybe literal MLIR interfaces too. So yeah, quick recap is on the slide. So we have 2 minutes, 30 seconds for questions.
Well, let's go through the recap still, you know. So dialect design is an art. There's no right or wrong answer. We can learn and try to make analogies with software design. You know, when people often ask, when should I use a dialect, or should I use a dialect here? And the question is really like, think about the problem you want to solve. Like, it's almost the same question where your library in regular software design becomes too big. When do you start thinking it should probably split? When is there scope creep in something? When is an API become too hard to use or to understand and should probably be split in 2 different API servicing something? You know, in software design, we have the single responsibility principle for classes, for example. If you follow very closely, you're going to have maybe too many classes. So sometimes it's a matter of design taste to fuse classes and not have denormalize your design. And that's the same for dialects. Sometimes people ask, why is this dialect doing this and this? Those are trade-offs. You mentioned the async dialect, which is a mix of 4 different dialects. But sometimes we do it because we don't want to have too many dialects. At some point, there's a cost to have too many abstraction, a complexity cost to mix and keep things documented and tested. So it's all about trade-off. There's not a single best design. We are still learning collectively. And so we're looking for your feedback and for contribution to start formalizing maybe or documenting those ideas. Right.
One day there'll be a book on MLIR. Thank you. That's it.
Thank you.
Any quick questions for Jeff and Mehdi?
I have a quick question. It's not a quick answer, I suppose.
Right.
Can we use any of that to simplify that horrible dialect diagram? We have like 35 dialects and like all this connection. Can we use some of like these concepts to simplify how MLIR is presented to users?
Yeah, I think so. I think that if you look at some of these complicated diagrams and you go, oh God, that's complicated, then I think that also is yeah, I think that's incentive that we should go in and really look at what's going on here, why is it so complex, and really start to pare it down to the basic principles.
I think one source of the complexity, though, is what I said about this being contextual. The SPIRV dialect can be presented on some use case as the ultimate output, and another one, the input, and you can make the same parallel with other dialects. There are so many use cases that it's really difficult. And that's what one of the difficulty about documenting MLIR upstream is that there is not a single pipeline in mind. LLVM, we have reference pipeline. We know that there's clang emit LLVM IR, and then we want to go to the backend, and this is fairly, there's one flow. And in MLIR, there's not one flow, and that contributes to the explosion, the conceptual explosion that makes it difficult to simplify a documentation, as you say. So we need more contextual documentation, I think. And that may be why ERI or XLA have better way to document, because they have a better defined flow. So that's just something to say.
Thanks, guys. Yeah, putting some sanity into all these dialects and stuff. You mentioned types as well. I mean, so one way one could see is like lowering of abstraction and types, like, so tensors, member F, vector. Would you guys be, tying this, what you presented, with the types and how would be very useful. But when I also think, the fewer types that way compared to the number of dialects that are out there, right? And why is that?
Well, I mean, one of them is that the built-in types is actually very multifaceted, right? Like, what is a tensor in a built-in type, right? There's also a sneaky metadata field in the memref and tensor types, allow people to turn these types into whatever they really need. And so I would argue that we do actually have more types than you can see, just because they share the same name and MLIR class and type ID, right? But they tend to be interpreted by different dialects in different ways. This is why some more newer infrastructures have gone the way of introducing their own tensor type, right? And so then when you actually bring these frameworks together, you have now an explicit challenge of I have a torch tensor, a TensorFlow tensor, a my tensor, an XLA tensor. And before, they're all just like tensor, 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 tensor with some metadata fields that makes writing passes a nightmare. So we do actually have a lot of different types, but when it's not obvious and encoded in the system, it actually leads to a lot of bugs and confusion.
Yeah, that's right. I think it causes confusion, like you said. But okay, I don't know. I don't have an answer either.
There's also a general reminder, which is when people ask, why is not X implemented in MLIR? The general answer that Alex gave is like, because no one added it or no one needed it. We do a lot of things on demand or based on what's needed. And also adding something into MLIR, the system upstream, requires some design work, because you have to think about not only your use case, but about how it's going to generalize. So often people add things in their system. There are many types that exist out of tree. Look at OpenAI Triton. They built, I think, a lot of their own thing without reusing too much of the dialects that are upstream, but they're using the infrastructure. And so that's the reason. Another thing, when you ask, why is it done this way? When you look at things that are very ingrained in the system, the answer can be history, right? We started with one standard dialect. We started with built-in type at a time where MLIR had no convenient way to add new type to the system. We didn't have an easy way to create dialect types before we added all those table gen facilities. And so the early days of MLIR were more monolithic, and we gradually modularized the system, provided extension points, but there are still elements of history that remains, like all the built-in types. Why is tensor and memref? Why are they built-in types? Why are they special? There's nothing that should be special about the memref type more than anyone else building their own buffer types, but history plays a role.
So let's thank Mehdi and Jeff one more time.